Okay. Third time's a charm. So in the last video I was working on where I was making this little 3.3 volt transformer circuit, I mentioned this in some capacity, and this is my first attempt on a prototyping board. Maybe not first attempt, but first completed project on a prototyping board. This is designed by me. You will see soon it is not designed by a professional. It was indeed designed by me. This is a manual EEPROM programmer, so this allows you to set a block address and physically bit bang across a data and clock line on two buttons and watch the data play back on LEDs. So whether it's input, output, whether you're putting the data in or the device is putting the data in, you'll see it on the LED. So it's pretty cool to sit here and try and manually write a word to it and then try and read that word back, and then when you get the acknowledge and then you pass the acknowledge and you see the 8-bit word play back on the LEDs that you put in there, it's very, very, very satisfying. So this is a 24C64. The reason I went with that is it's because it's one of the first sizes of EEPROM that requires a 2-word data address. So you'll have an 8-bit word that addresses the device, an 8-bit word that addresses the specific address on the device, and then you'll have an 8-bit word that is data input or output. But once you get over a certain size of EEPROM, you need more than 8 bytes for a data address if you're trying to get up into the upper addresses. So what they do is this one particularly will take a 13-bit address, and the way it does that is it'll take an 8-bit address to acknowledge the device, and then it will take 3 bits that make no difference. It does not care what those first 3 bits are. Then it will take 5 bits, completing a 8-bit word, and then it will acknowledge and then take the last 8 bits. So it's in total a 13-bit address device. The only reason it's that way is because of the capacity. Like I said, you have to address those higher addresses somehow, and the only way you do it is by going through 2 different words. So this also has write protection, switched power. On the side here, you'll notice there's a port. This actually takes a CMOS battery, laptop CMOS battery. That's the actual plug, so you can buy these wired batteries online. I made this one up out of a couple 2032s because it works way better with 6 volts than it does with 3 volts. I think the minimum voltage for this particular chip is like 3.5 volts. So once you get down that way, it starts to not acknowledge as often as it should. So you get a lot of errors that way. But with the 6 volt, it has no problem. Even when this double cell battery gets low, it still works fine because it's well above the 3.5 volt threshold. And you can turn on set write protection and just read. So if let's say I was pulling an I2C EEPROM out of anything, pulling an I2C bus out of a radio. Okay, if I had an EEPROM in a radio that I wanted to pull out, and the radio had some sort of key, like the Chevy radios, for example, they do have 24C08 actually that has the key to the VIN number of the actual car that the stereo was installed in. So obviously if you bought a radio on eBay, unless it's unlocked, it's not going to work in your car unless you pay lots of money for somebody to reprogram through the OBD port, I believe, the radio to your car. And all they're doing, you're spending all that money just to access this one chip. So what people are doing are buying these radios, pulling the EEPROM chips out, throwing them in EEPROM programmers, finding the area where it has the VIN number for the car it was installed on, changing that VIN number or removing it altogether, finding some bypass method on the either hardware or software, and getting it to run on any car. So this is just one example. These chips are in everything. So if you wanted to pull it out and see what's on it, you can do that. So the way this is wired here I've got 2 rails hung across the complete board at the bottom. The back rail is negative, the next rail is positive, and you notice the positive rail does go between these buttons here. So this is about as compact as it gets. And I tried writing down, drawing top bottom diagrams of this thing, and I knew it was possible, but no matter how I laid it out on paper, I couldn't get it to work. I just kept getting lost in the rails and jumping over the solder points and things. So technically, the only line jump solder on this thing is this right here. This is the negative for the battery connector, and that could have been a big old squirrely wire with the plug for all I care. So technically, this is a 1-layer PCB. This could all be done on a 1-layer PCB of relatively small size, no problem. It basically is here. So you have 2 rails, positive and negative. You have the battery connector. The battery connector goes directly to this switch on the positive, and the positive goes actually to the other side here, where the positive is pulled up for the positive for the chip, so that this rail up top actually supplies positive to the chip, and that is where the other side of this switch is jumping to. And these buttons here are jumped to negative on the back side, and on the other side they're jumped to data bus and clock bus on these pins. You can see they jump across here. One comes across this block address switch, one comes across right here. That's data and clock, and I have a couple 0.1 microfarad capacitors across those buttons just to help debounce, and they actually seem to work relatively well. And then I took the some 10K resistors, which these EEPROMs, any datasheet you look up is going to tell you to pull the line high. It's an open drain, so you actually supply a source. You pull the line down and release it and pull it back down for a clock pulse. You don't press it and release it for a clock pulse. You press it to make it active, and then you release it and press it again, bringing it high and low for a clock pulse. So it's kind of backwards, but it starts to become relatively simple as you play with it. And the write protection here is the rails jumping to the top, and on the other side is jumping to the negative. So if this switch is up, it's pulling the write protection pin high. If it's down, it's pulling the write protection pin low from this rail. Here is each line, data and clock, pulled high through a 10K. I have a button on each to pull each low when needed. And then off of each line, data and clock, I have a 100K going to the base on an NPN transistor. The collector on the transistor is tied low through these rails up top here, and then the base or the emitter of the transistor is then going to the low side of the LED, and the LED going down is tied to high over top here. So the way I hung this positive rail underneath here, I was able to pull it up through, jump across the pads on either side, and go to the LEDs hot through another hole there. When I pull it low, it turns the transistor off. That turns the LED off. So when the line's low, the LED's low. When the line's high, the LED's high. It's just using the transistor as a switch and the low resistance to actually not interfere with the bus. So from that, we have the 3 block address pins here. Now, block address, when I first started playing with I2C, I was mistaken. So I thought the block address was separating chunks of addresses within the device. That's false. The block address is specifically for hardware addressing. So if I wanted to hook a bunch of these 24C64s up together, I'd make sure each one had a different block address. That way, if I wanted to talk to one, I'd type in its block address for the block address. If I want to talk to the other one, I'd type in a different block address. So it's specifically for multi-device communication. The block address has nothing to do with the actual device operation. So I could have just as easily pulled all of these address pins low and just made sure that I put zeros in for the block address. And it would have worked no matter what I put in here. But the reason I did that is because I want to pull the lines off of here somehow later on. So if I had a cell phone dead open here, I can say pull these lines off, right? So if I found say a gyroscope in here, an I2C gyroscope, I could power it, pull the datas and clocks off of this pin, and make sure that it's all the same power, all the same, using the same power and the same data and clock, and I could bang data out of the gyroscope and bang it into the EEPROM. So I can pull data off of devices that I have laying dead on the floor. So that's later on, obviously, that's even over the scope for what I understand, but that's just, I figured that would be something cool to look into later. Pulling data off of dead tech with a manual EEPROM program, I think that would be pretty cool. So I'll have a full schematic of this thing up. It's pretty tedious as far as soldering goes. You get a lot of points where once you get it too hot, the solder mask starts to kind of fade, and you get the solder jumping across the solder mask where you don't want it to. There's a lot of places here where it's really close. And I thought when I first made it, I was having issues where I'd pull either of the lines low and the data LED would flicker. And I found out that it was a dead resistor, but at first I thought I was having problems with capacitance between the actual solder points, because when you get two plates, capacitor, period. So I thought there was actual capacitance going on in my circuit because my solder was so close to itself. So I promise you, you build this, by the time you're done, you'll be good at soldering. That's not a joke. If you get this done, you will have enough soldering skills to go out and do pretty much anything through hole. Anything through hole. Okay, and including desoldering. This came with, what did this come with? Flux? This either came with flux or solder, I can't remember, maybe both. But I used this several times in the making of this. I'd put a big glob of solder between something, and I'd realize that one side was jumped and it wasn't supposed to be, so I'd have to heat it up, suck a bunch of solder off, and then fix the solder. Or later on, after it was done, I noticed there'd be like right here, a big glob. I could heat that up and pull some of the solder off. Even though it's still soldered, I could pull some off just to make it cleaner. So yeah, you'll have a lot of practice soldering and desoldering. So if you want to build this thing, I would get that, I would get that, I would get that, I would get that, and that. You could build this whole thing with that. As long as you have the parts here, this is all you need. Soldering iron, solder, flux, you don't need the battery, of course. Solder suckers, highly recommended, cutters, and tweezers. So like I said, I'll have a schematic up for this thing. I'll show you it working here. Make you work for it. Let's see. 6-volt double 2032 cell. Make sure it's off. Don't want no voltage spikes here. Critical hardware. We'll have a turn on. Turn the right protection on. Make our block address 100. And the way this particular chip works is you do least significant byte first on the block address. So instead of typing in 100, we'll actually be typing in 001 for the block address. So with the data sheet open in front of me, it's not. I learned this by heart by this point. But I'll have the data sheet in the description. You're more than welcome to look it up. You'll see that when the data is pulled low while the clock is high, you have a start condition. All devices on the bus are now looking for a specific address, an acknowledgement address that tells the device that it's being talked to, that it's the device on the line being talked to. So we'll go ahead and pull the clock line low just so we can get ready. Now this is a non-busy state. So we'll go ahead, we can, now that we have the clock low, we can do anything with the data, makes no difference. So we'll do 1010. That is the specific acknowledgement address for all I2C EEPROMs. Now we'll be doing the 3-bit block address, which, since we have least significant bit first, it's 001, so we'll do 001. Now we have our read or write pin, or read or write byte. So what I'm going to do is put in a 1 so we can read whatever current address it's on. Now that you've seen the clock bang, that clock pulse through for a 1, as soon as I pulled it back low, the device itself pulled our data line low. Our device knows we're talking to it. It's ready for data, it's ready for acknowledgement, it's ready to put out data, receive data, whatever. So what we've just done is a start 1010 EEPROM, 001 for this EEPROM, 1 read, and acknowledge. So now it's at acknowledgement condition. We'll go ahead and bang the acknowledge through. The line has now been let go by the EEPROM, and it's ready to output its data. So what you're looking at here, because we were doing a read, this is the first bit of the EEPROM's data. Whatever address it happened to be started on, which is address 000 or 00, whatever the first address is on the EEPROM, I just turned it on, so that's what it's at. This is the first bit, so we bang the acknowledge through, the device will let the line go, and because we're reading, the device will put data out. So we don't want to pull this line low while this device is trying to put out data. If this line pulls it high and I pull it low, or vice versa, it could cause damage to something. Likely not, but it could. So now we'll go ahead and start banging the data through. I'll read it out as we got it. So we have a 1, 1, 0, 0, 1, 1, 0, 0. 11001100. That is the 8-bit word that happened to be stored on the first address of this EEPROM. So now that we've brought data out of the EEPROM, if I just sit here and keep hitting clock pulses, the EEPROM isn't going to do anything. There are parts to the protocol that have to be completed in order to get more things to happen. So I'll leave you to go to data sheets and stuff and figure that out. But for now, what we want to do is stop. So we've started, we've addressed, we've read, now we want to stop. And the way we do that is the reverse of a start condition. So we'll pull both low, let clock high, and bring data high while clock's high. So for a start condition, you bring data low while clock's high. For a stop condition, you bring data high while clock's high. And that concludes a whole current read operation. So as you can see, when we go through it, it's very easy to mistake bytes or let the line up on accident. So when you're putting in data, you'll have a lot of times where you're putting things in and it's just not happening. So I actually have a single cell battery around here. When you plug that in, 3.3 volts ain't enough. So I can get it to acknowledge maybe 3 out of 5 times, but 2 out of 5 times are errors. So that's totally not feasible in a situation where it's running at its typical 400 kilohertz or whatever the maximum speed is of this thing. So you want it to be at enough voltage, and 6.5 volts is the maximum volts for this thing. This thing's at like 6.2. No, it's just taped on there. So, but yeah, this was a fun little project, and it took me a while. It took me a while to get it working. It took me a while to get everything soldered on it, but now that it's done, I'm pretty proud of it. So I'll have the schematic up, and yeah. I want to stress, if you are super frustrated with soldering, if you just can't get it working, I'm willing to bet it's probably your equipment. If you put a legitimate effort into it, multiple times tried to become a feasible solderer, a feasible tinkerer, and you just can't get the solder to flow, you can't get things to stick, I'm promising you, buy some new solder, buy a new tip for your soldering iron, and try some flux. You'll start to get the hang of it, because if you're not If your equipment is malfunctioning, you're not getting that feeling. You're not getting the feeling of the soldering melting through the hole. You're not getting the feeling of how much solder it really takes to make a glob on one hole. You're not learning these things. You're not learning how much heat. You're not learning how long to keep the soldering iron on it. You're not learning how much solder, flux, how often to clean your tip. These are things you have to learn, and if your equipment's malfunctioning, you're not going to have a normal circumstance. You're going to be struggling. If you're using beat up pencil solderers out of the garage, it's not going to fly. So get some new tips, get some new solder, try some flux. I promise you, you will not be disappointed. Yeah, thanks for watching. Take care.